All right, welcome everybody to the HAO Colloquium. I am delighted to welcome Professor Leon Offman here to give us a colloquium. Let me tell you a little bit about Leon, who I've known for many decades now. He received his bachelor's degree in physics and his master's from Tel Aviv University in Israel, and his PhD in physics from the University of Texas at Austin. He had an NRC postdoc at NASA Goddard from 1992 to 1994. And since then, he has continued working at NASA Goddard as a contractor for Hughes and Raytheon. And in 2001, he became a research associate professor at Catholic University of America and an associate professor from thereafter. And he's an affiliate at NASA Goddard to the present. He has been since 2007 a visiting associate professor at Tel Aviv University, and in 2009, a research professor at CUA's Department of Physics and Institute for Astrophysics and Computational Science. His main research interests are in solar plasma physics, MHD, waves and instability, and kinetic processes related to coronal heating and solar wind acceleration. And his main expertise is in the numerical modeling of the solar coronal and wind plasma, driven by space-based observations. He's authored and co-authored over 450 publications in solar physics and related fields, and he is the principal investigator on many NSF and NASA grants, supervising postdocs and students. He was a member of the science definition team for Solar Probe Plus mission, Parker Solar Probe now, and of course has served as a referee and reviewer in many journals and funding agencies. He's a member of the American Astronomical Society Solar Physics Division, the AGU, the IAU, and COSFAR. Welcome, Leon, and today he's going to tell us about new views of the solar wind formation and origin from the Parker Solar Probe.
Thank you, Sarah, for the nice introduction. I didn't even remember all these things. And thank you for having me here. I am delighted to be here, as always, when I visit AGO in Boulder. I'm going to present a colloquium on new views, the solar wind formation and origins from the Parker Solar Probe. This work was done in collaboration with my former postdoc, Yogesh, is now at University of Iowa, and a number of people from Goddard, as well from other universities, like Georgia State University, Johns Hopkins, APL, as well as University of Arizona. So first, give you a brief overview introduction. I'm sure some of you are familiar with these pictures, but anyway, so we have the solar wind as we see it, as it was been seen by Ulysses spacecraft. It consists of two main modes, the fast solar wind, as evident here during solar minimum, where it's mostly dominated by polar regions, coronal holes. And during solar maximum, we have a highly variable wind that also is coming primarily from streamers. And you can see the variability, the correlation with the solar cycle. Paper from McComas. But we still have some big questions on the solar wind, still unresolved, even though it has been studied for decades. Of course, we are now as close as ever to answering those questions of how the solar wind is formed and accelerated from a few kilometers per second near the solar surface to about 1,000 kilometers per second in the heliosphere. And how is the solar wind plasma heated so much from 6,000 Kelvin to millions of degrees? So now, of course, we all know about the solar activity as it manifests itself in two main events, which are flares and coronal mass ejections. As you see, an X-type flare on the left, and the coronal mass ejection on the right, followed by impact of charged particles to the detector seen by solar spacecraft. So all of these activities that are, some of them may be geoaffective, that means affecting our space weather environment, and so on, they propagate in the background solar wind. So, for example, arrival times of CMEs, as well as the motion of charged particles, is determined by the solar wind. So we need to know or have better picture of the solar wind in order to have good predictions. So solar wind, as very basic conceptual view, this is from the science definition team report for the Parker Solar Probe. So we have this region of acceleration. You see the solar radii close to the sun, from a few kilometers per second to about close to 1,600-700. And in this region, solar wind is the propagation speed of the solar wind is below the Alfvén speed. The Alfvén speed is denoted here, is determined by the magnetic field magnitude over the square root of density is proportional to that. So you can see that above sort of about 10 solar radii, the solar wind becomes super-Alfvénic. That means most of the acceleration happens here in the sub-Alfvénic origin solar wind. However, previous missions only, and also the acceleration of solar energetic particles happens in this region mostly. So previous missions explored only this region in the super-Alfvénic solar wind, mostly. Although there were sporadic detections of sub-Alfvénic wind, but mostly was super-Alfvénic. Okay, and Parker Solar Probe is the first mission that entered the sub-Alfvénic, the birthplace. So, okay, so what is Parker Solar Probe? Just a reminder for those who are not directly working here. So it was launched in 2018, and it's the first ever mission to touch the sun. That means it would literally enters the solar outer atmosphere, the corona, and the closest perihelion was not that long ago in December 2024. Well, there were about more than 20 perihelia since the launch, but the one in December was the closest approach to less than solar radii. So it travels directly through the solar atmosphere with a suite of instruments that provides unprecedented data on the solar wind. And not only global data, global quantities, moments, but also details of the velocity distribution of the ions. One of the main goals of the Parker Solar Probe was to trace the how the energy flows from the sun to the solar wind and accelerates the solar wind. So far we have about 150 gigabytes of data. The mission was recently extended, regardless of all the uncertainties at recent time. It was extended to 2029. And it had already so far 25 perihelia, as I mentioned. We also have to remember that there is a complementing data from ESA's solar orbiter. I don't have time to go into that, but it also provides data in the inner heliosphere and as well as outside of the eclipse. Anyway, so this is the Parker Solar Probe launch and orbits. So how did it get so close to the sun? It used Venus as gravity assist flyby. So there were about 7 Venus gravity assist flybys. It's also the fastest man-made object, reaching perihelia at about 200 kilometers per second. Okay, and the orbital period is about 88 days. So you can see this is a picture that shows the heliocentric distance as a function of time. This was in January, end of January, so you can see where the Parker Solar Probe is, and these are the orbits you can see here. So what are the instruments there, and which ones, are relevant to the solar wind? Of course, all of them are relevant one way and the other, but most directly relevant to the kind of work that I've been doing is the fields instrument that basically measures the magnetic field and the Poynting flux. It also measures the plasma density and electron temperature. Okay, and then we have the ISIS investigation that measures the energetic particles. This is also very interesting and useful data. Then we have the WISPER, the wide field planetary wide field imager of the solar probe, that basically shows how the disturbances from the sun propagate outward, such as CMEs, in great detail. They're seen in situ by this instrument. Of course, the instrument is directed away from the sun, not to be blinded by solar light. And there is the sweep instrument, which is the most relevant to the kind of investigation I've been doing of kinetic instabilities. So it has detectors that measure basically eventually provide the velocity distribution by measuring energies and so on of electrons, protons, and alpha particles. And you can see the PI here. So this was the first light in 2018. Of course, the Parker Solar Probe was far from the sun compared to where it is today. But you can see the Earth, and this is, these were the first images that showed that the instrument works, and it was the CME that, it was able to track the propagation of the CME at that time. Now, since then, of course, this is in a recent encounter. We have much more detailed picture, and you can see here how the sun first, how it grows in size because of the approach. Here's the heliocentric distance is shown somewhere here, distance, yes, in solar radii, and this is the speed of the spacecraft. So it's amazing to see all the, the streamer structure. Of course, there is some processing here, but still it shows you the streamer structure, as well as you will see a CME that's going off at very great detail. Okay, something that is, unprecedented. You can also see some evidence of likely Kelvin-Helmholtz instability, as was reported in some recent papers. There's a comet passing by here. So this is really amazing data that complement the data from the field and particle detectors from the point of view of studying the solar wind. Okay, so this is, just in December last year, no, 24, sorry. In December, there was the first closest approach. It was Encounter 22, where the spacecraft approached to 6.1 million kilometers. It's about 9.86 solar radii. And here is an animation showing, visualization provided by NASA of the event. And this is the orbit. So that's what we have now. So it will continue to do these elliptical orbits, at least until 29. It will be analyzed. I hope it will be extended farther than that. But anyway, so this is from the recent encounter. Again, you can see from the close approach, you can see the detail of the CME and the structures were unimaginable before. So anyway, so what are the important discoveries made by Parker Solar Probe so far? So that the sun has a dust-free zone at about solar radii. There are the magnetic field switchbacks illustrated here by this. Okay, there is the transition to turbulence in the solar wind outfield. As you can see here, and I'll talk a bit more about this, the turbulence is changing as you go farther out. It's not the same spectrum. Then there's the small-scale energetic events and ion beams and kinetic waves near the sun. I will gonna talk more about that. And detection of the subalphenic solar wind. So going back to the switchbacks, this was reported in Nature in 2019. So basically, if you look at this schematic picture, you see this of potential extrapolation. But what happens here, you have these changes in the direction of the magnetic field, very rapid changes as the solar wind propagates outward. And there, as the spacecraft travel to this region, you can see the magnetic field direction switching by 180 degrees. Okay, so this is the BR. Okay, and then in that paper by Bale et al., they traced the location where are these field lines coming from, as we see in this picture. So that was the idea here.
Can I ask a question?
Sure.
Or we wait until the end?
Yep.
Okay. The filamentary structure deep in the corona becomes turbulence. Is there a characteristic distance at which that happens? You clearly see the filaments disappearing.
Well, which filaments are in?
Well, the videos that you showed clearly showed filaments.
Right. So you have the streamer's structure, but then after about 10 solar radii, they all kind of merge. You don't distinguish them as much as you can see closer to the sun. Right.
And that would be where the turbulence zone would kind of begin.
Yeah, the turbulence would change there and the wind becomes more turbulent because also the background magnetic field becomes much weaker as well. So it's the structures are much less organized by magnetic field. So they are just turbulence where the magnetic field and the plasma are frozen in. So they rotate in these big cells that go to smaller and smaller scales.
Thank you.
You're welcome. So these switchbacks, basically, there is evidence that they are alphanic. There's high alphanicity. That means there is a correlation between the magnetic field and the velocity perturbation. You can see here, this is on the left are the velocity components, on the right are magnetic field components. The correlation is very, very strong.
Can you point out the switchbacks on that plot?
Well, if you look at the radial, yeah, this is, you don't see that much, but you can see that the BR is changing very strongly in direction. Okay, so that may be, if you look at BR here, there's becoming positive and it's negative right here, for example.
Okay.
Yeah, and here as well, because this is zero, so it's somewhere here.
So the blue is VR and the red is
Yeah.
VR. Okay.
And the interpretation is that these are localized kinks or twists in the magnetic field. It's not like a global structure, the switchback.
Well, that was my next slide. This is from NASA infographics. So this is basically a collection of all the possible explanation, but I added another one here, the one that is just flew in here. It wasn't there. It should be. So basically, after those switchbacks were discovered, there were many explanations that were proposed, and I think some of the obvious ones were missed. Okay, so for example, there could be like reconnection field lines, interchange reconnection, creating switchbacks, okay, or some flux ropes. Then I guess the expanding plasma ripples that may be closely related to the Alphen waves that I'm going to talk next line. Okay, there is the velocity shift driven turbulence and slow wind reconnection to fast wind, where the fast is overtaking the slow wind. Okay, so anyway, the idea that most interests me was that these are basically manifestations of very strong alphanic fluctuations. And this is basically connects to the model done in collaboration with Davila in '97, where we basically modeled nonlinear Alphen waves in the solar wind Okay, and that was part of work related to basically for a future probe mission. And there we sort of suggested that they may be detected in situ. Okay, these large variations in the parallel magnetic field velocity could be possibly detected in situ by the proposed solar probe. Okay. Anyway, so my favorite interpretation is that these are alphanic fluctuations that drive basically nonlinearly fluctuations in the parallel component of the velocity, right? That's okay. So the next aspect, which is I already touched upon, is the detection of the subalphanic wind. Okay, so here this was a paper by Casper et al. In 2021, again, where they reported for the first time, and here you can see the Mach number, which is the ratio between the solar wind speed and the local alpha speed. The Mach number equals 1, denoted by this dashed line. So we can see periods denoted here by this gray shaded area of subalphanic wind. Now, of course, we have more, later time, there were some additional periods. This is another paper by Bundy et al. So there were plenty of evidence of subalphanic wind periods. Now, only now we're starting to understand that the subalphanic wind has some different properties as far as kinetic instabilities and switchbacks are concerned compared to the subalphanic wind. So, for example, this is from a recent paper by Mustafavi et al., which I co-authored as well. If you look at the temperature anisotropy of protons and alpha particles on the left, okay, and as a function of radial distance from the sun, okay, you don't see any organized picture here, okay. However, if you sort of present the same data as a function of the French Mach number, you clearly can see, okay, that the difference between the protons and the alphas and how it depends on the Mach number. So you can see that initially the protons are isotropic, then their temperature anisotropy, the ratio between the temperature parallel and perpendicular to the magnetic field, starts to increase, and it actually peaks somewhere near Mach number equals 1. Okay. The other hand, the alpha particles are the mostly anisotropic at lower Mach numbers, and then the anisotropy starts to decrease farther from the sun. Okay. So it tells us that the processes related to the perpendicular heating and cooling of these ions basically depend on the Mach number more clearly than on radial distance. Okay, so now what are these anisotropies if we look at them in more detail in the kinetic scale? Okay. So what is shown here on the left, this is from the paper by Near et al. 22. It shows the typical best example of VTF, where you see three parts. You can see here the core of the VTF that is not isotropic, because you can see this oval. Basically, the temperature perpendicular to the field is higher than the parallel field. There's of course some missing data and so on. Then you see the beam structure here, and then sort of the hammerhead, which is like the hammerhead shark, so something like that. So here, this is highly anisotropic region where you have diffusion of the particles in the perpendicular direction. Okay. Similar picture is also seen for alpha particles, but you can see here how the this perpendicular anisotropy depends with the ratio of the density in this population here. Okay, with respect to the total density. Okay, so you see that, of course, if you have some density where the anisotropy is the largest one, and then as the density increases, becomes less anisotropic. Okay, and this is the function, the drift velocity of the third population with respect to the core. So now this is in counter 17. You still see these structures. This is, you can see this anisotropic core, the beam, and hammerhead. Some data here is missing because of the occulter. There is effect of the thermal shield of the Parker Solar Probe. So some of the data, cannot enter the detector. It really depends on the orientation, the magnetic field, and the shield. Because when the Parker Solar Probe is at close approach to the sun, all the instruments are behind the shield, and the reason we can still see those velocity distributions is because the magnetic field lines are not, are at an angle with respect to the spacecraft. They carry the particles in. Anyway, so the turbulence in the solar wind, that was the previous picture on the left. We had this picture of scaling. So we had there's the energy containing range of f to the -1. Then there is inertial range when there's no dissipation in this range. Okay, this is all ideal MHD. And this from several spacecraft, as you see from ACE and Cluster. Cluster when it enters the solar wind. Okay, then there is the dissipation range, and this is where the energy can basically convert to heat. But this happens somewhere near the gyro frequency of the protons. Okay. Now, on the right, you can see results from Parker Solar Probe. So, and this is from Solar Orbiter on the right, on the far right, this panel here. This is 0.11 AU, this is 0.88, 18 AU. You can see that the slope is changing. Okay, it's not the same for these two figures. And this is just a sketch showing what kind of resonances we can have. So we have the ion-cyclotron resonance, and if we have a magnetosonic wave, it is not resonant with the ions, but it does resonate with the electrons. Okay. So now we see, this is from Chenadel. We see this picture from Parker Solar Probe where the color table shows the distance in AU. And you can see how the turbulence is changing. Okay. From -3/2 slopes to -5/3. The -5/3 is dissipationless, so there is some dissipation going on close to the sun. So, what about the kinetic wave? So now we have the kinetic wave activity that is measured in the solar wind. It was also measured far from the sun by, for example, by wind spacecraft. And what was found is that when we look at the number of measurements we have in the anisotropy versus beta parallel phase space, we can see that most of the measurements are inside this region, inside those curves that provide the marginal stability for the anisotropy, for these kinetic instabilities, the cyclotron mirror and the various Firehose instabilities. So that strongly suggests, or maybe not strongly, I don't know. It definitely suggests, though, that these instabilities can play a role in the formation of and the heating of the solar wind. And of course, if we have some parcel of plasma, for example, that is formed really far from these curves and it's highly unstable, then very quickly it will end up in the range of stability. Okay, so with respect to Parker Solar Probe data, so in the subalfinic solar wind, what we see here is that the VDFs already become different. We don't see as much beam structure as we've seen in the encounters farther from the sun, where there were more beams. But here we see more anisotropy. The structures are anisotropic. So let me explain briefly what this graph shows. This is the Mach number, where the blue line shows m equals 1. So anything under this blue line is the subalfinic wind. This is the magnitude of B. Okay, it doesn't vary by much. Okay, it varies quite gradually. So most of this Alpha speed is determined by the variability of the density, basically. Right? And compared to previous old picture where we had some nice surface, alphanic surface, that was thought to be at 20 solar radii, or maybe it was elliptical or something like that. It's actually the structure of the alphanic surface is highly irregular. There were several recent papers showing the structure of the alphan surface. So it's really a very complex surface. It's not really a surface, but very jagged structure of the transition between the subalphanic and superphanic.
So the bottom axis hours that X
Yes.
bottom x-axis.
Yes, it is ours. This is on February 25, 2022. Sorry, these are small. Right. But in the subalphanic wind, we see very strong anisotropy. Okay. And this is, for example, again, we see some evidence of beams, but the beams are weaker. So this is log scale, so you can see this beam. If you remember in the first picture, the beam was, when the number of particles was comparable to what we see in the core. But here they are all on the log scale, several orders of magnitude below the core density, phase space density. Now, what happens when we cross the current sheet? Okay, or when Parker Solar Probe was near the current sheet, here is again some data of the magnetic wave activity, and we can see that there are various waves mode that basically compressional versus transverse waves. We can see the variation of the magnetic field component. This is very high resolution, tape resolution in seconds. You can see very high variability of these waves. And this is the frequency spectrum. This is the cyclotron frequency here. Okay. So when you approach the current sheet, the Mach number here is increasing for the obvious reasons that magnetic field becomes quite weak, okay, because it's reversing. So then the Mach number here is large. Okay, but here it is, as you approach the current sheet, it is subalphanic on both sides. Okay, so this is also an interesting picture. So here you can see really the details of the ion scale wave activity during this period. And this black line shows where this VDF is obtained. So you can see there are a lot of power in polarized waves. Okay, in this case, they're right-hand polarized. And if you look closely, this is, okay, this time here is minutes, but here is in seconds. Okay, fractions of seconds, in 2 seconds. You can see the evidence, direct evidence of ion cyclotron waves. I can plot a hodogram which shows the rotation of the magnetic field vector. It's almost like in a textbook. See the rotation of your wave vector. Okay, so there are just several cycles, but the amplitude is changing. But you can see very good, phase shift that shows the circle polarized waves. Okay, so how do we approach to better study these kinetic waves and stability? So one way is to do a hybrid peak model. So basically, in this model, we take the particles, the protons and the alpha particles as particles in a particle in cell approach. The electrons, which evolve on a much faster time scale, are modeled as a fluid. This is done by neglecting their inertia and deriving generalized Ohm's law. Okay, and you show the Maxwell equations supplemented by that. Then you can also include an expanding box model. That means because the solar wind expands as it travels away from the sun, schematically shown here, basically the coordinates perpendicular to the direction of magnetic field are getting stretched. So this is very sort of, just a basic approximation of how the solar wind expands. And this is important for the estimate of the perpendicular heating and so on. Because the expansion basically causes perpendicular cooling, adiabatic cooling in the perpendicular direction. Anyway, so there are some technical details about the model. So how do we proceed with these models? So in the model, we can initialize our velocity distribution directly, okay, by providing the distribution of particles. So we have in our initial state, for example, we have here proton core and proton beam. Both of them are Maxwellian in initial state, and these are the alpha particles, okay? And the parameters of the core and beam are taken from Parker Solar Probe, from measurement of Parker Solar Probe, but whatever was the beta there, and the abundance of alpha particles, there were only 4.5% alpha particle. Okay, so then we know from linear analysis that this VDF is unstable. This is solution of linearized loss of dispersion. Okay, shows that at K, at normalized K at 0.7, this is the fastest growing mode. So this situation will be linearly unstable. But linearly doesn't provide the whole picture. So we run this model with our nonlinear hybrid code. And this shows the evolution of the beam after several thousand up to nearly 6,000 gyro periods. You can see that very quickly this initial state is changing both for protons and alphas due to the generation of waves and scattering. So the instability grows and becomes nonlinear. So eventually particles are scattered from the beam towards the core. This process is faster in protons compared to alphas. For these parameters, of course. So we can look at the evolution, because in the model we can separate the core and the beam, and the revolution we are in the solar wind frame, as opposed to the Parker Solar Probe measurements spacecraft frame. So the plasma is moving through the detector, so we're not measuring the same plasma as a function of time. Okay. Here we are sitting in the model in the solar wind frame, and we can calculate the anisotropy, the beam and the core as a function of time. Here you can see the dashed line shows the effect of the expansion, how the expansion. So these are expanding models, and the non-expanding are shown with this thin line. So you can see that the evolution is faster in the expanding model, not by much, but over several thousand gyro periods, the effect of expansion can build up. So you can also look at the separate energies of the core and beam. So you can see that the core is losing energy in the parallel direction, while the beam, the proton beam, is gaining energy in the parallel direction. And this is in the perpendicular direction, the core and the beam. So again, the core is losing energy. So basically the beam is gaining energy. So we get the picture so that the core is providing the energy to the beam, and for the alpha particles, they basically gain their energy from in both directions because they absorb some of the energy emitted by the core of the protons. Okay. Another interesting aspect of these wave-particle interactions are the oblique modes. So when in a simple linear picture, your modes, your waves are growing only for given kx, and ky is basically 0. But what we see here that initially we do generate quite a strong spectrum of waves for ky non-zero for oblique waves. Okay, and then as the evolution proceeds nonlinearly, these modes dissipate quite quickly, so we end up with a lot of power in the parallel direction near the where we would expect from the fastest growing mode, about 0.7. Okay, and then these waves get dissipated as well, so they in the more unstable case, this process is even faster. Okay, so then we can look at the dispersion relation. If you remember graduate plasma physics course. So this is the dispersion relation obtained from the hybrid model. So it's just actually taking these perpendicular magnetic fluctuations. Okay, this is for parameters obtained from encounter 11. Okay, and you can see several branches. So first you see the very strong power. Yeah, the scale shows the power here in the resonant branches. This is the proton resonances. The reason we see this symmetric structure is because we have waves propagating in both directions in our model. Okay, but actually what we would be interested is in half of this space for k greater than 0. And you can see evidence of these resonances of alpha particles, although they are much weaker. We only have 5% of particles in this model. But still you can detect it from the thing. And here you have some absorption going on, possibly by the alpha particles of the part of the spectrum of the waves. So if we repeat the same model in 3D hybrid, which is more computation intensive, we see very similar evolution. Here we started with stronger drift of 2.5 often speeds. So the evolution is faster, but very similar structure to what is seen in 2.5D. Okay, and this is the velocity space distribution. So we start with this cyclophonic solar wind, where we have just an anisotropy, but then we can also build a beam in the alpha particles, okay, because of the wave particle interactions that scatter some of these waves that accelerate the alpha particles in the parallel direction. Okay, so here I'm showing you the results of the hot beams action. So in previous model, we had basically cold beams, but where beta was much less than 1. In this more recent work, we introduced initial anisotropy of 2 based on what we see in solar wind, and also looked at beams with higher temperatures. So here you can see the evolution of the alpha particle beam as it becomes more heated in the perpendicular direction. The core is slightly heated, and then for the protons, they are both basically lose energy as a result of this evolution. So these are the protons, okay, the initial state, and the final state. Basically, we see that if we look in here, then the anisotropy is decreasing for both the core and the beam, as well as the temperature is decreasing. And you can look at the energies of the core and beam, so you can see that the main source of energy is the core of the protons. So when the protons become anisotropic, they lose energy and provide free energy to the heating of the alpha particles. Okay, so let's skip that. Yeah, so also if you look at the drift between the various particles, they also, between the protons and the alpha particles, and so the drift is decreasing as a function of time. So that's another source of free energy, is the initial drift, as we've seen in the solar wind. Eventually, that drift generates spectrum of waves, as we've seen in the model, and these waves basically get absorbed, leading to decrease in the magnitude because they scatter these particles towards the core. And this is just for various parameters, various initial states, as indicated here for different values of the drift. Okay, so the protons had 2 alpha speed, the alphas 1.4, and different parallel betas for each case. Okay, so now how these beams are generated in the first place, this is still an open question. So one of the possibilities to generate these beams is by initial wave spectrum. So for example, when we discuss the turbulence, okay, eventually some of the turbulent energy can lead to acceleration of the wave. So here is initial wave spectrum that is used to study the generation of the beam. So you can see that this is our initial state, is nearly isotropic, and then in the final state we start to form these beams already after 600 gyro period. So that would be about 6 seconds, right, depending where we are in the sun. But then we see this evidence, this plateau region, which is very typical of the beam formation. Okay, and this is the total anisotropy of the structure. So initially it's close to 1, but then as the beam is forming, then the total anisotropy becomes less than 1 because the VDF is extended in the parallel direction compared to perpendicular. Of course, if we separate the core at the beam, we would see that this is not true anisotropy of the full population, but just the effect of the beam. Okay. Yeah. So this is in 3D hybrid model showing the formation of the beam in the alpha particles. Okay. Again, by this process where we have a different process where we have free energy coming from strong proton anisotropy, then gets absorbed into alpha particles and formation of the beam. Now, as I mentioned at the beginning, we had quite a lot of data, gigabytes of data from partial solar probe, and some periods are show evidence of different instabilities, different kinetic instabilities. Some periods don't show it. So the question is, how do we identify and classify those instabilities in the data? Because manually it would be, a tough job. So one way to do it, or maybe the only one so far, is using machine learning. So we take basically the problem with machine learning is that you have to train the machine learning first. Okay, so you train with some data that with known properties. Okay, the way you get the data, basically we take our hybrid modeling results. So what we have done, basically, we use the results of the many hybrid models and about 1,600 VDFs to train machine learning, deep learning algorithm where I have several layers of neural networks. Okay, and then we can apply, and now we're working on that, to real data, the train algorithm to real data, and then the final goal is that we would classify, okay, the instability, so some kind of instability A, B, C, and all this blue dots would be the observed VDFs. Okay, So these are some first results that were published by Sadiqov et al., one of my collaborators, where we tested this approach. Okay, we tried to identify kinetic instabilities using hybrid peak models. So we divided our results into, training data set and then the unseen data set. And what is shown here are various types of machine learning models. Some of them use just the moments of the VDFs, and some of them use the VDFs as images. Here it just shows the resolution and velocity space of these images. So what is shown here in this table is basically the various parameters of the results of the identification. So TP is through positive cases, through negative, false positive, false negative. And this is accuracy, and this is total stress score, which means how good the model is. The closer to 1, that means the better is the result. Okay. Now, because in the nonlinear evolution, we have to think of what would be the characteristic to decide if our model results in a stable evolution or not. So one way to do it is a similar approach as used in the glass where we have margin stability. Usually it's set to a growth rate of maybe 10 to the minus 3 of the JR period, something like that. So we use the same criteria, but in the nonlinear stage where we took some quantity and look at the evolution of this quantity with time. So in this case, it could be either the temperature anisotropy or the electromagnetic total energy in the magnetic fluctuations. So this would be the criteria. Okay. And out of these models, the best result was obtained using the random forest classifier approach. Okay. The other ones are also quite good, but not as good as the random forest. So, to summarize, okay, we have a Parker Solar Probe provided major new discoveries that basically revolutionized our view of the solar wind close to the sun in the observation region. One of the important things my point of view was the finding of kinetic wave activity and the ample evidence of ion kinetic instabilities. Okay, so using these discoveries and data, we model the solar wind using the hybrid model, so where we can look in detail for various cases of VDFs, how the energy goes into the different parts of the velocity distribution. It's either beam, the core, the parallel direction, the perpendicular direction. And these are basically consistent with linear stability analysis, but of course the hybrid models extended to nonlinear regime, so we can look at the nonlinear evolution. And we find that the results of the models, the hybrid models, they are consistent with what is seen in Parker Solar Probe observations. It was lots of papers. We have also developed machine learning algorithm in order to identify these periods of instabilities and classify them. First step was to use the hybrid modeling results, and now we are applying it to real data. And with real data, of course, we have several issues like noise, and then the fact that we have the occulters, velocity distribution could be missing, so it has to be reconstructed. So we have to prepare the data for machine learning before it can be successfully used. So that's it. Thank you very much.
Thank you. Questions?
I'll ask you for a second. The instabilities that are responsible for the plasma heating. in your simulations were looking at the temporal evolution. So is it the case that the evolution of the time scale, the growth rate, inverse growth rate, is much less than the time for the change in the beam configuration, core versus beam, like convective growth versus temporal growth? Know what?
Well, I'm not sure what you mean the time scale is less. The thing is that when you are looking in the Parker Solar Probe data, you're in a spacecraft frame. So you are not looking at the evolution of the instability, but only at a snapshot of the results. Okay, there are some periods, by the way, where the ESP is traveling with the background wind, but those are just a few of these periods. So your plasma is moving past the detector, so you get continuous snapshots of the plasma. Now, in the model, we can, that's the only, I mean, given that we have a single point observation, so only in the model we can look at the VDF that is measured by Parker Solar Probe as our initial state. Okay, so more simplified approach that was used previously was taking that initial state and sticking the, for example, temperature and isotropies into a linearized loss of dispersion. Okay, and then you can look. So in if an isotropy is such and such, and the other parameters beta is so and so, you can calculate what would be the growth rate. Okay, and we can see from these Brazil plots with the marginal curves that show that most of the plasma is in a stable state. So if it's unstable, it very quickly moves to the stable state. Okay. Close to the sun, you see more evidence of instability. But plasma is unstable towards these linear, even linear stability conditions. With the hybrid model, you can evolve these initial VDFs from observations, motivated by observations. You can evolve them in a linear regime. So we can also calculate the output spectrum and then how the spectrum is reabsorbed. It can be, let's say, emitted by protons and reabsorbed by alpha particles and result in the heating of alpha. This you cannot put it directly in the linear regime. Okay, you have to do a linear study. So what our models show is how this energy, the initial state, motivated by Parker Solar Probe, how the energies, go to waves from waves to different type of particles, then can be re-emitted again, and that VDFs again reaches new equilibrium. Does that answer your question?
Maybe my question was a lot simpler in the sense that
Sorry for complicating things.
this instability occurring, the core beam configuration is evolving as it moves in, and there's a time scale for the instability to manifest, change the distributions. Assumption is that's happening or observationally, maybe you verify it's happening very quickly on the scale on which that evolution occurs. So you can treat it locally as a local instability.
No, it's not that quick because we have very good, it happens on the time scale of seconds. Okay. So our temporal resolution is better than a second. Okay. So we can those VDFs can be measured very quickly. So they're not steady in that sense.
So I have a question on a bigger scale, and that is, do these beams, are they sustained to much larger radial distances, or are they are they observed at 1 AU, or are they wiped out by 1 AU?
Well, they are definitely observed by solar orbiter.
Okay.
Yeah.
At larger radial distance.
Yes. So the solar orbiter is maybe at 0.6, 0.7 AU. They are observed there. Very clear. There is also evidence from wind, but wind doesn't have wind spacecraft. Wind spacecraft doesn't have that high resolution velocity space as you have from these newer spacecraft. But yeah, they are observed.
So
My question would be, what is your expectation? How far out these wave modes would be identifiable?
I think they would be identifiable to 1 AU and beyond, but their role is different. Okay, because in the close to the sun, the spectrum, there's more energy of kinetic waves. Okay, compared to, let's say, the kinetic energy in the solar wind. So they are important energetically. The farther from the sun, there would be there, but they would not affect the velocity distributions as much, like being absorbed or emitted and so on. So it all happens to close to the sun in the subalpinic region where you have the accelerations happening. Then when the solar wind is coasting, there is less smaller effects.
So, and this is now, I feel, my naive classification, there is the fast solar wind and the sort of more regular solar wind. So these kinetic waves, are they in the fast wind?
Well, the Parker Solar Probe doesn't measure fast wind that much.
Ah.
Okay. So, but I would say that some of that we would expect in the fast solar wind, we would expect even more waves happening. So, with in the open field arena.
To continue on about fast solar wind, proton temperatures are very elevated in fast solar wind compared to electrons.
Yes.
Does the Parker Solar Probe or your kinetic instability analysis show more evidence for proton heating than electron heating?
Well, yeah, because this all these processes are ion heating, proton and alpha particles.
So does the Parker Solar Probe measure electron heating?
Well, it measures the electrons. It doesn't measure heating directly. This is the inference from the modeling. It just provides you a snapshot.
Yeah.
Okay, so we don't know what. I mean, we need to do some modeling of theoretical analysis to know what process led to this VDF and kinetic wave structure. Okay, and if there is temperature anisotropy, that is, you have a high hypercritical temperature, because we know that close to the sun, due to collisions, the plasma is isotropic in temperature. Okay, well, we don't know it directly, but spectroscopically, maybe we can deduce it. So farther out, the anisotropy is increasing, while the result of expansion is supposed to decrease, but it actually is increasing. Something deposited energy in the perpendicular direction. In the in the fast solar wind, these processes are likely to be stronger. But as I said, because Parker Solar Probe doesn't measure the fast wind, maybe there were some periods, I don't know. But as far as I know, there were no measurements of the fast wind. There are measurements or they expected to be measurements from Solar Orbiter because it is going out of the ecliptic plane. Okay. Yeah. On one hand. On the other hand, Solar Orbiter is much farther out. So,
What about a large, low latitude coronal hole? There's been some doozies lately.
yes, so there were coronal holes. So this is sort of called a slow fast wind. Yes, because
But right at the center of it, I imagine it's still
Yeah.
pretty fast, right?
it is not as fast as fast wind. So
Not like the
so
poles where you're way away from the boundary.
yes, so in coronal holes there is strongly alphenic, which has a lot of the same properties as the fast wind, but because of some processes of interaction with surrounding plasma and so on, it doesn't reach the same speed and properties as the fast wind that comes from polar coronal.
Actually, let me ask you a leading question then. So Ulysses was at 5 AU or something, 4 or 5, it was pretty far out.
Yes.
Do you think that a solar polar mission with an in situ solar wind monitor would see something fundamentally different? If it was able to look much closer to 1 AU in its orbit?
So definitely, okay. 1 AU is maybe not,
You need to go closer?
yeah.
Okay.
So first let me tell you just very couple sentences, brief history of Parker Solar Probe. Before it was designed to be equatorial mission, it was designed to be actually polar mission. Okay? So that was the Parker Solar Probe without the plus. But what happened was that this kind of mission would have been much more expensive because you have to send it to Jupiter and back to get it out of the ecliptic plane.
Right.
And then there will be only maybe a couple of flybys.
Yeah, I remember. Yeah.
Right. So then NASA asked the science definition team a new mission, equatorial mission, also using Venus as gravity assist. Okay. So there are trade-offs. There were definitely, as you've seen, big list of discoveries, and also we have the fast light solar wind coming from equatorial coronals, but it does miss, I would say, the full fast wind physics by not going through the subalfinic fast wind.
But
Maybe-
Ulysses with that.
Well, Ulysses did it, but it went, it was very far away where wind was already fully accelerated. Yeah, so these processes, maybe there were some indirect evidence of the process that led to the acceleration, but it's not the same as going into the acceleration region, in the sense of getting evidence. What is the kinetic physics going on? What is the power spectra of the waves, polarization, the VDFs, and so on, as we see in this study that I showed you.
Have we learned anything from the Parker Solar Probe about global modeling of the solar wind? Because you're in so close.
Yeah, so you can see, if you're talking about global models, then most appropriate is to look at the whisper. Okay, because they show you kind of structuring. And I think that the current global models do not include all this fine structure of the streamers, Kelvin-Helmholtz instability has its own.
But on a much more kind of global scale, with every passing, right, every encounter, there's been predictions, model predictions that have been compared to what they're flying through. And I've got to think, I don't know if this has been demonstrated, that the models with that much validation at that level, it's got to be having an effect on the quality of the global models too, right?
Yeah, global models, again, we're talking about, if you're talking about the single point measurements, is not enough to get the.
Right, but for every, you know how it is, every single encounter, there's a whole suite of models that are being thrown at it, and they're saying, okay, this is what you're going to be flying through, and then they check it and so on. And so this is, Sam Badman's been doing work on this.
You can, definitely there were attempts to use Parker Solar Probe to validate and calibrate global models.
Yeah.
Yes, but I think that in global models, they're intrinsically missing the kind of complexity we see. And this is not because they don't know about it, it's just because it's technically not feasible to include all these structures and details in a, in a 3D, especially 3D models of how many cells we have, won't be enough. Computation would be very demanding, if not impossible, to include the kind of structuring we see from Whisper, for example, that I showed you in the beginning of the talk. Right? And they would affect global models, yes, these structures. Not global, I mean the global structure of the true heliosphere. But in the models, we'll not be able to capture it.
Questions? Aligned with this? Do you have any questions? If not, then let's thank our speaker again.
In that movie you showed at the beginning with the, can you show the whisper movie again? Were those all, what were all the